Okay, welcome, Sarah and Megan, and welcome, Chan Mary. Thanks for coming. I'm going to share my screen so we can talk about the plan today. Okay, so the plan of the day is first I will answer questions as always. We always start that way. And then we're going to move to pretty much, I'm going to say the rest of the course, and that is hypothesis testing. So hypothesis testing is a really, really important piece of statistics. Okay, we're only week 7, and we're spending the rest of the entire course on hypothesis testing. So obviously it's important. So we're going to be doing the most simple hypothesis testing we can do in this chapter, and then we're going to kind of add and tweak it each time, each week. So there are some uses of what we're doing this week, but the main thing is to understand hypothesis testing so that you can do what you need to do to decide or make a conclusion. And this is all about making conclusions. Whereas confidence intervals were all about estimating and saying, well, I think it's about here. I might be off by this amount. Now we're going to say, well, I know I have evidence that this is true. And that's what hypothesis testing will be all about. We'll talk about type 1 and type 2 errors. So again, you have evidence that it's true. So you're going to make that decision. You're going to move on it. But as hopefully you know, anytime you take a sample, it may not be right. And you might screw up and then you got an error. So we'll talk about those errors. We'll talk about the level of significance. And that comes from the idea of the type 1 and type 2 error. Then we'll talk about the p-value, and that gets a little complex, but it's important. It's one of the main things in hypothesis testing. So each of these items you definitely need to understand. Then we'll talk about how do you state your conclusion once you've conducted your hypothesis test, found what we call the p-value, and then how do you proceed. Then we'll get into some details, kind of like when we had confidence intervals. Remember, with 95% confident, we can say that between blah, blah. That was kind of the important part of the confidence interval. But then there was that little fine print on what does it mean to be 95% confident? So similar, we're going to say, well, what does it mean to have this p-value? And p, by the way, stands for probability. So what does it mean to have this probability? Then we'll interpret the level of significance. Okay, which turns out to be a type 1 error, by the way, or the probability of a type 1 error. But we'll talk about how to use it. And then once we're done talking about this chapter, we're in chapter 9, by the way, we will get into the project. And we'll talk about the project, how to plan for it, where you should be now, how you should move forward, coming up with ideas, what you should focus on and not focus on, et cetera, et cetera. And I'll be happy to, answer any questions about it too. So that is the plan for today. So let me ask you, are there any questions about anything? Okay, and as always, this is your chance. So if you have questions, please ask. If I don't hear any questions, then I'll move on and talk about the new material. Okay, let me ask you a question. Do you remember, or have you heard about the scientific method? I think you first learned about it in middle school, actually. Who remembers what the scientific method is? Be great if you can tell me, because you learned it, you've heard it. Otherwise, there's something wrong with your, middle school teacher. I know it might have been a while ago. I have no idea how old any of you are, but but some of you might have been a long time, some not so long. You remember the scientific method? I don't hear you all jumping in. You put in the chat box, you say it. Okay, I'm not hearing it, so maybe I'll just say it to remind you, because you have heard it. Okay, maybe you don't remember it completely, but the idea of the scientific method is you start out by coming up with a hypothesis. You decide what you think might be right. You say, I think this is what's going on in science or psychology or what business or whatever you're doing, medicine. This is what you think is going on. So that's your kind of first step, is to come up with your idea, which we call a hypothesis. And we're going to state what's called the null hypothesis and the alternative hypothesis. Okay. And what hypothesis testing is all about is the scientific method. Okay. It is doing the scientific method, but formally statistically. So the first thing you do is you state the null hypothesis. And the null hypothesis is what you're hoping to refute. So you're trying to, you might think that, people aren't getting enough sleep. Okay. And enough sleep is 8 hours of sleep a night on average. So the null hypothesis, people are getting 8 hours of sleep on average. Okay. And in particular, it's quantitative, so it'd be mu equals 8. On the other hand, the alternative hypothesis is what you're trying to show. And if you think people aren't getting enough sleep, then you're trying to show that mu is less than 8, because that was what your hypothesis is. So the first step is in the scientific method is to decide what your hypotheses are. Okay. And again, hypothesis testing, which is what pretty much the rest of the class is all about, is the scientific method. So that's your first step, is state the hypotheses. Then after that, once you've stated your hypotheses, then what you usually do is you plan. You decide, well, how am I going to collect my data? How am I going to run my experiment? What am I going to do? What's going to make me decide to say yes? You just make a big plan. Then after you make your big plan, then you go ahead and get your data. That data might be in a survey. It might be some kind of chemistry experiment. Who knows? But you're going to collect data. Then the next step after collecting the data is you do your calculations. So we're going to be doing calculations. We're going to find what's called a p-value. We're going to say, what is the probability that the data that we collected is so far away from the null hypothesis that it's not very believable. The null hypothesis isn't believable. And then the last step is to say, well, if it's that low a probability, it's not believable. So therefore, the null hypothesis is wrong. And the alternative hypothesis, I got evidence for it, and I'm going to say it's right. On the other hand, if the probability is not that low, you say, well, it is believable. And you know what? Maybe the null hypothesis is right. I give up. Okay. I bow my head down and say, no, I don't have it. And you don't publish a paper. You don't do what you need to do. Any questions on that idea? Any questions? Okay. Let me give you one that, and a kind of an example, just kind of a general example that you've all heard about. You've all probably watched TV on, and maybe you've experienced. I've experienced it. And that is a court case. Okay. If you have a court case, the first thing that happens is you're selected, basically. Okay. And if you're on the jury, we're going to talk about being on the jury. So the first thing that happens is you get the null and alternative hypotheses. Okay. And the null hypothesis, okay, that comes from who? Who's going to tell you the null hypothesis?
The question from the other person, or the data from the other person?
Okay, I like Mary, the lawyers, but in particular, not just any old lawyer. The null hypothesis is going to come from the defense attorney. Say, hey, this person's not guilty. Nothing really happened. This person was just normal, right? Or this company, this company's food was just fine. Those people didn't die because of the food. They just died because they just died. Does that make sense? If it was something like that. Okay. And then the alternative hypothesis would be the prosecuting attorney. And the prosecuting attorney is saying, are you kidding? This company, they're giving out poison food and everyone's dying and they need to be held responsible for it. Does that make sense? And that's the first step is you got, your defense attorney and you got the prosecuting attorney. Okay. In a court of trial, you tend to do the alternative before the null, but in statistics, we do the null before the alternative in terms of the way we write it out. Okay. But they're written together. Okay. Then the next thing you do is then you hear the evidence. That's collecting the data. You listen to all the data. Okay. And that's all the witnesses, right? And the witness is going to say, hey, look, we had 300,000 people and 1,000 of them all died. Okay. And of course, the defense attorney would say, well, that could happen. People die. But then the prosecuting attorney would say, no, they died because of this. That's a much higher that's a much higher number that would die normally. Okay. And then what happens is the juror, okay, which I've been on the jury. They have to say, you know what? There's a strong probability, really, really high probability that this really was poison food. Okay, bad food. And the jury has to say guilty. Or they're going to say, well, I don't really have enough. There's not enough evidence. It could have just been random people dying, and then not guilty. Okay. But you actually don't say not guilty. Okay. Okay. You just say you don't have evidence to show they were guilty. Okay? That's how it really is. Even though you hear the words not guilty, but really is not evidence. And I will tell you personally, the one trial I was on, there was a decent chance that the person was actually committed the crime, but the evidence wasn't there and the probability didn't show it. Okay. That doesn't mean the person didn't commit the crime. It just meant that they didn't have enough evidence to say that the person committed the crime. Do you see the difference? And when we're doing a hypothesis test, you either say guilty, which means that we're going to say the alternative hypothesis is correct, or you're going to say we don't have enough evidence to make a decision. Any questions on that idea, kind of the court system way of looking at it? Figure I picked that one because that one's, most people are familiar with it. Okay, and I'm not saying you've been on a jury, but you've probably seen it in TV or something. Okay, any questions on this idea? Okay, so let us look at an example. And I want to show you how to do research. Okay, so this isn't necessarily statistics, but this will actually help you with the discussion post that you have to make. So I want to let you know this week's discussion post, you're not looking for a newspaper a newsletter, a news article. You must find a peer-reviewed journal article, which is very different. So don't go to gallup.com because that's not a peer-reviewed article, that's news. Okay, instead you go to peer-reviewed. Where do you think there's a really good collection of peer-reviewed articles that you have access to, all of you?
Library.
Exactly, the library. Okay. And when I say the library, I mean modern library, which means the library's website. Okay. I think you're allowed, I think you might even be allowed to go to the library now, but the website is what you want to go to. So what I did is I went to the library's website and I found a good article actually. And what I did is I just copied and pasted the title of the article. So when you have to go find your article and you find an article in the library, don't give the URL. The URL doesn't work, it turns out. Okay, the URL's got all kinds of issues. It's just gonna, it usually doesn't work for you. Instead, post the title of the article. So the title of the article I looked at is the relationship between perceived psychological distress, behavioral indicators, and African-American female college student food insecurity. So it was an interesting article, and I'm going to show you how to find it. So the first thing is you go to the library. And by the way you go to the library is you go to LTCC's website. And at the top, you'll see the title library, and you click on library. And ltcc.edu is a website. Then what you do is you go to find articles. So I clicked on that. Okay. Then you hit academic search per year. Okay. It's going to ask you for your username and password. Okay. And that's your login when you went on to Canvas and when you went on to register for this class. So you hit login. And then there's a search. And I copied and pasted the title. And I hit search. And most of the time will be the first one if it's the whole title. It's only going to find that one because how many articles have that title? Usually just the one. I'm going to click PDF full text. And I just want to show you what articles look like. I'm not sure if you have read peer-reviewed journal articles before. Have you guys read those before?
No.
Okay, well, it's time. Okay, that's called college. And you're college students, so especially when you get into upper division, and this class, a big part of it is to prepare you for upper division classes. Okay, so here's a peer-reviewed journal article. I'm not going to read the whole article for you because it goes on and on and on, but I want to mention some things. Okay, if you look at data for the methods, data for this cross-sectional study were collected among 112 HBCU full-time female undergraduate students in Southwestern region of the United States. Do you think that's a big sample, by the way? We can go back to our old stuff now. Big sample, small sample? What do you think? 112?
Small sample?
Yeah, this is a pretty small sample if what you're looking at is qualitative data, like a yes/no question. If it's quantitative, it's actually pretty big. But it turns out this was pretty much all qualitative data. So this was actually a small sample. So this is not the best article because of the small sample. I want to point that out, even though it's not what we're doing necessarily today. That was what we did in the first week of class, but it is important. Okay. And for example, lastly, the substance abuse inventory was assumed by yes or no responses to the following 11 questions. So again, it's a yes, no question stuff. So worry a bit, but I want to show you because it's all over the place. If you go to results, okay, and they have variable, you have N, you have the percent of the people who said yes. And now let me read what it says. Okay, I know this might be a bit small, the font and stuff, but I'll read it to you so at least you hear it. As shown in the table 2, differences in psychological behavior, inventories, and food insecurity status were assessed using independent t-tests. So independent t-tests, that's going to be one of the major tests we're going to be using today is t-tests. Okay, next week we'll do independent sample t-tests, which is a little more what they're doing, but I just want to show you what these kind of things look like. Okay, participants with food insecurity were significantly more likely to have used drugs in the last month. P less than 0.05. I want to focus on that. Okay, so P less than 0.05. That's that P value that I talked about a little while ago. That means you have a small probability that had the population not been what they said it was, in other words, been the same whether they had food insecurity or not, then there would be less than a 5% chance that we would get such different numbers, 2.5 versus 1.53, than what these authors got in their sample. Okay, then they do more with more p less than 0.05, and more p less than 0.05, and more p less than 0.05. Okay, then in the table for substance use, they give you a t negative 2.25. Remember students' t distribution, that's that value. And then the p value is going to be the probability of being less than that value. And if it had a single asterisk, they're telling you p is less than 0.05. If it has a double asterisk like this t, then p is less than 0.01. Okay, on the other hand, this guy with personal conflict resolution, that says that we don't really know whether that has anything to do with substance abuse, okay, and all this other stuff they're looking at. Okay, any questions on kind of the idea? Again, I don't expect you to understand every detail of it, but I want to show you what articles look like. And this is what articles look like. So you're going to, by the way, for your discussion post, you're going to have to find an article that gives a p-value. And then you're going to post it, and then someone else is going to have to conduct the entire hypothesis test, which is what we're doing today, is how to do a hypothesis test. So what I want you to do when you do your post is make sure that you can answer your own. Don't answer it for everyone else, but just do it on a piece of paper. If you can't do it on a piece of paper, it may not be a good post. Okay. Any questions on kind of reading these articles? So journal articles are sophisticated. Okay, this is how they are. And part of being a college educated person means that you can read journal articles. Okay, it doesn't mean you ever understand everything about them, but you can read them. Any questions on this? All right, so let's go on. And I can talk about other examples. Okay, and this is an example, this is a personal example, and I'll explain why it's personal in a bit. And that is, does average pH in the streams that flow into Lake Tahoe differ from 7.0? Okay, let me tell you why this one's personal. I'm not sure if those of you who are Tahoe people know what happened on Saturday. Something called Snapshot Day. Have you heard of it? Okay, if you haven't, that's okay. So let me tell you about it. Snapshot Day, what it is Keep Tahoe Blue actually is the one that right now is the one that's organizing it. And they get a bunch of volunteers to go out to the creeks that flow into Lake Tahoe to collect data. And there's a lot of creeks, so they get literally like 100 volunteers. Okay, and as you might guess, I was one of them, not because I'm a statistician, but because, I don't know, it was fun. I got to go to the creek and enjoy Tahoe and feel like I was part of this big effort, which is, you know, scientific and, you know, helps understand our lake and any issues we might have. So one of the things that I did for one of the creeks, in fact, I looked at two particular areas of the upper Truckee River. If you don't know what that is, that's okay. But it's a river that goes into Lake Tahoe. And I literally took off my shoes and got into the water. It was cold, as you can imagine. I put in a pH meter and I got a pH for where I was. Okay. And this was done all around Lake Tahoe, and it's been done for 21 years. Okay. So what we want to find out is, we have this thought is, well, is the pH in Lake Tahoe different from 7.0? And I don't mean in Lake Tahoe, but in the creeks that flow into Lake Tahoe. And I'm talking about the population mean pH over all the creeks over, you know, all 21 years or whatever, you know. Does that make sense as an idea? 7.0 chemically is what water is. If it's pure water, you get a pH of 7. Okay, and if you don't know chemistry, that's okay. You don't need to know it, but you just trust me. Okay, so here's what I can do. I can write down my null and alternative hypotheses. So let's do that, because that's step one. Step one is H naught. And H naught is that the population mean pH is 7. And hopefully you all know the symbol for population mean is mu. And that is equal to 7. Any questions on stating what's called the null hypothesis? Okay, I want to mention something important. And that is H stands for the word hypothesis. And we always use capital H. Sub-zero is always null. Okay, we call it null and not zero typically, or not. And the reason is the British got to it before the Americans. And if you've ever been to England, they don't say zero, they say not. That's just the way they say it. So everyone in statistics uses H naught. Then you put a colon. Always have a colon. Don't put H naught with an equal sign. It's H naught with a colon. And then you put in your parameter variable. So in this case, it was a quantitative study, so it's mu. Had it been a yes, no question, what do you think it would be instead of mu? Right, the data I got when I put it in, and I got 6.7 for the pH when I looked at the upper Truckee flow at that day on Saturday. But had it been a yes, no question instead, what would we use instead of mu? So what letter to use for yes, no questions? Very important.
P?
Yeah, P. Good, good. Very important to get the right letter in. I take off points on tests if you put the wrong letter in. So if it's a quantitative question, use mu. If it's a yes, no question, use P. Okay. We'll have other examples next week and the week after that. Each week we're gonna have different stuff. But for this week, it's mu and P. Okay. And notice it's never a sentence here for this chapter. It's always symbols only. Then we're gonna have H. There's two ways of writing it. I'm gonna write it as H1 with a colon. Some people write HA instead of H1. A for alternative, or 1 because 0 then 1. And that's up to you. You're responsible for knowing how to read it. However you want to write it is up to you, whether you want to write 1 or A. It's done both ways. Okay, then we're going to write mu again. All right, now we want to show if it differs from 7. That's what our hypothesis is. Our alternative hypothesis is that it differs from 7. What symbol do you use to represent differs? What's the mathematical symbol that means differs or differ? And you should know, it's not very fancy. You know this symbol.
Not equal to?
Exactly, it's the not equal to sign. So I'm gonna go to not equal to 7. Okay, first thing is this is a two-tailed test. And the reason we call this a two-tailed test is the not equal to. Because for it to be not equal to something, it could be very low or very high. And then it's not equal to. So not equal to means either to the left of or to the right of. Does that make sense, or is that confusing? Okay, and I'm not going to draw it, but if we drew a normal curve, then not equal to means left tail or right tail and not in the middle. Do you see? Any questions on that idea? Okay, the next is we're going to talk about what the errors. So let me write down type 1 error. So let me give you in general. What that means, a type 1 error, means you reject the null hypothesis when the null hypothesis was true. Rejecting the null hypothesis means accepting the alternative hypothesis. Okay, so what that means in terms of our example is we're going to end up publishing, okay, or whoever's in charge, of the doing the final science stuff, they're going to publish that the pH is different than 7.0. Okay, it's maybe acidic or basic is what that means chemically. But actually it wasn't. It was 7. It was a pH of 7, which is like great for life. Okay, but they're going to publish it isn't. And that's bad. An error is always bad, by the way. Okay, so in this case, they will publish that the pH is not 7 when it really is. Okay, and I should say, I guess, the population mean average pH. Because remember, mu is a population mean. Population mean, I don't need average again. So the population mean pH is not 7 when it really is. Okay, that'll cause problems. What do you think will happen in a bad way if this happens? If everyone decided that the pH is not 7, what's going to happen? Any thoughts? Let's see you jumping in. Okay, what'll happen if we decided the pH was not 7, we're going to say we got a problem here. Okay, we got acidic water, we got basic water, and life isn't going to make it. Okay, so guess what? We're going to put a lot of money into it. So a lot of money will go into trying to make the pH go back to 7. But it was 7. It was already 7. So we totally wasted our money. Is that bad? Is that a bad thing?
Yes.
Yeah, that's a bad thing. Wasting money is a bad thing. Okay, when it could have gone to other good things. Okay. All right, that's a type 1 error. Okay, let me boldface type 1 error because that's important. Let's do type 2 error. Okay, type 2 error is you fail to reject the null hypothesis, when the null hypothesis was false. Or let's write when the alternative hypothesis was true. Okay, so in this case, that means that we will not have evidence. Let's scroll a bit so we can keep it. So we'll not have evidence to conclude that the pH is not 7. And it wasn't 7. Any questions on that? All right, is that bad? What bad thing will happen if we don't have evidence to say that there's any difference from 7 in the pH? But guess what? The pH might have been 4 or something like that. So what are the bad results? Sometimes we'll call those the repercussions. Any thoughts? So what will happen in a bad way? Let's see you all jumping in. Okay, if the pH isn't 7 and we don't do anything, what's going to happen? Let's see y'all jumping in. Okay, if you have a high acidic water or high basic water, then the life, let's go native, life in the lake will die out. Is that a bad thing?
Yes.
Yeah, that's a terrible thing. Okay, we have an eco disaster. Any questions on a type 1 versus a type 2 error? All right, now if you look at these, you say, which is worse? Do you think the type 1 or the type 2 error is worse? Which do you think is worse in this case?
Type 2?
Yeah, I think type 2 is, but I'm an environmentalist, okay? You know, it depends whether you care about your money or whether you care about the environment. For me personally, I think type 2, I live in Tahoe. I live here for a reason because I love nature and I don't want to destroy nature. I'd rather spend a little extra money. So notice that a type 2 error is worse. All right, so what does that tell us? Well, here's what we do, okay? So if they're the same, we set the level of significance to be 0.05. Remember, we had confidence intervals, kind of similar to that, except for some reason, don't get mad at me, I'm not the one that made this decision. With confidence intervals, you talk about the probability that you're right. With hypothesis testing, you talk about the probability that you're wrong. Sorry about that. But it's just the way all the statisticians do it. So we're going to use 5% as the standard. So 5% or 0.05 if they're the same. If type 2 is worse, let's go type 1. Then use 0. Let me write down actually, just so you're used to the letters. The letter we use is alpha. Use alpha equals 0.01. Okay. On the other hand, if type 2 is worse, then use alpha equals 0.1. Okay, a type 1 error turns out to be the probability that alpha is the probability of a type 1 error, but it's a give and a take. Okay, so you don't want a very high chance of a type 1 error. if a type 1 error is bad. So that's why you set it to be low. Okay, whereas type 1, if type 2 is worse, you say, well, I'll give up some of that issue with the type 1. Yeah, you're going to have a higher chance of a type 1, but now I'll have a lower chance of a type 2. By the way, if they're both horrible, for example, an example I like to give is a vaccine, then what should you do? Let's look what they're doing right now, and that is testing to see about the vaccine for children. Okay, for young children. Okay, right now they're doing tests on that. And if they're both really bad, okay, and they are really bad, right? Because kids die either way, then what should you do? And we've talked about this with confidence intervals also. Do you remember what to do if either way is bad? Same as confidence intervals. Can you remember? Not hearing y'all jump in, so maybe I'll tell you. So you increase your sample size. So in other words, something like the vaccine, you don't want to give it to every child in America if you have a small sample size. Because what if it really does cause horrible problems and you're killing 1 million children? That's like the worst imaginable thing. So what you do is you don't unleash it to the entire country until you have very good evidence on both sides. Any questions on that idea? Okay, so in this case, let's use, so type 2 is error, we're 0.1. Because type 2 is worse, and we decided that type 2 is worse, use 0.1 or 10%. Any questions on this so far? So I'm going through a whole hypothesis test. Okay, so the next step, by the way, I want to let you know, this is a step-by-step process. The order is essential. You change the order at which you do things, and you're not doing correct science. Okay, you have to do in the right order. You don't go and do all your data collection analysis until after you've made all these decisions, and then you do your data collection analysis. So the next step is you do your data collection. Okay, and I'm going to have to tell you for this one, which is okay because I'm going to show you this anyway, is I was able to get the data for this. Emily Fry, who's actually in charge of this project, she sent me the data on a spreadsheet, and it had like 500 data values. So my calculator doesn't work well with 500 data values, but my other calculator does, and that's the spreadsheet program you use for the project, which kind of coincidentally, or maybe I don't know if it's coincidentally or not because I planned it, is that I set it up so that we're going to be talking about the project anyway. So let me, oh shoot, let me go to it. It's so hard with Zoom. I have to go click on things and. Thought I put it in there. Let me go back to my drive. There we go. Okay. So because there was so much data, I used a spreadsheet program, the one I wrote, the one that you do your project on, and I put the data in. And by the way, literally this goes up over 500 because they've been doing this for 21 years. Okay. And here we have the data. Notice that there's some places that had pH of 6.75. This was perfect 7. Here's 8.4. So there's all kinds of different pHs. We look at the average. The average is important because it's all flowing into the lake and it averages out. So, because it all mixes. So the nice thing about the spreadsheet is you don't have to do anything other than put the data in. So I put the data in. I do have to decide H1. It said mu question mark mu not, and I'm going to turn it into a not equal to sign. And when I do that, I get a p-value of 0. What does that tell you? Okay, that means you have a very, very small probability. Okay, close to 0. And it's not exactly 0, but it's so many decimals, the spreadsheet can't even handle that many decimals. It just rounds to 0. Okay, I don't remember how many, but it's over 10 decimal places, I think. So it rounded the p-value to 0. It is tiny. So because the p-value is small, so let's go back. So we got our p-value. Was less than 0.1, because that's our key value is 0.1 is what we called our level of significance. And we decided on that right here. Because the p-value is less than 0.1, here's the conclusion. There is statistically significant evidence to conclude that the population mean pH in inflows into Lake Tahoe is, or let's go, differs from 7. I want to highlight population mean. That's necessary. Just like confidence intervals, it's all about the population mean for this particular example because it is quantitative. So I want to stop. Any questions about this conclusion and what we just stated? Okay, I want to mention something, and that is that we have statistically significant evidence. So we call this statistically significant. Here's what we don't necessarily know. Does it mean that we have a big problem? That we don't know yet. And this is where, let's go back to the spreadsheet and notice that the, oh, you know what? I forgot. No wonder why it's 0, because I thought it wasn't. It says, I forgot to change that mu naught to 7. That changes everything. But P is 0.004. I'm going to go to 3 decimals. Sorry about that. So P is 0.004. I made a little error. I forgot to change. Mu naught is the number on the right-hand side of the equal sign in the alternative hypothesis. And that was our pH of 7. That was our status quo number. And our p-value, sorry, was 0.004-ish. So let's go ahead and put that in just a minute. 0.004. Which is definitely still less than 0.1. So we still can say this. I made one little error. Sorry about that. All right, so next, if I go and look at this, by the way, the mean was about 6.9. And here's a question. Is 6.9 dangerous? And I'm not asking you. I'm not going to tell you the answer because I don't really know for sure, because I am not, I'm not a environmental scientist. But if you're an environmental scientist, you better know, because that's your job, not mine. I don't pretend to know everything. But the question is, if 6.9 isn't a dangerous issue, then we say we have statistically significant evidence, but we don't have practically significant evidence. So the question is there a practical issue? We definitely have, it's definitely not 7, but is it far enough away or not. And that's where confidence intervals tend to help. Just want to mention that. Okay, so there's a difference. We know that it's not, we have evidence, statistically significant evidence, it's not 7, but we have not said how far from 7 it is. We just know it isn't 7. Any questions on that? So that's just a note, and very important to note when you're doing your projects, by the way, because your projects are going to be about confidence intervals and hypothesis testing. Any questions on this example?
Yes, Larry, I have a question. So did you say type 2 error is always worse, or is that a judgment?
No, type 2 error was worse in this case.
In this case.
Because to me personally, it may not be worse to you, right? Because you're going to have to pay more taxes for no reason if there's a type 1 error, right? And some people don't like that. I'd rather pay a little more taxes to have an environmentally good place. That's just me. So that's a personal thing, which is type 1 and type 2. So when I ask you, by the way, I'm either, if you said type 1, that's fine too, as long as you have a good explanation. And if your explanation is, I think it'd be awful if I had to pay more taxes, that's a lot worse than a few little, fish dying. Who cares about the fish? If that was your feeling and that's what you put on the exam, I give you full credit. Does that make sense?
Okay.
So again, that's a personal thing. So for the exams and for the discussion post, for example, you have to explain your reasoning. And that's the important thing. Talk about what the issues are with type 1 and type 2, and then bounce them out and explain. Any questions on that idea?
So if in this example, we decided that type 1 was worse, does that change the alpha value?
Yeah, right here.
Oh, it does.
Look, that's right here.
Mm-hmm. No, I meant
Type 1 was worse, we'd use alpha as 0.01.
mm-hmm.
Okay, now in this particular case, either way you would have rejected, and you would have said there's statistically significant evidence, because had I changed this 0.1 to 0.01, 0.004 is still small enough. Do you see that?
Yes. No, my question is that even if like you determine type 1 or type 2 is worse, but the alpha for type 1 and type 2 is always the same value, 0.01 and 0.1?
In our class, yeah, and that's
Okay.
pretty much the way it is, and 0.05 if they're kind of balanced. 0.05 is the standard, just like 95% confidence is a standard. So for our class, we're going to be looking at this way. Okay.
I understand. Thank you.
There are fields where 0.001 is used, but again, this is elementary stats, so I want to keep it simple. Does that make sense? So don't get mad at me if you go to graduate school and they use something slightly different, because that field might be a little different. But this is used more often than not. Okay, good question though. Very good question. Any other questions on this so far? All right, so now that we have this conclusion, so that was the main thing, by the way. So I want to do the following. I want to emphasize it. I'm going to make it big. And then the next stuff I'm going to make small, because the next stuff isn't as important. I'll test on it, but there'll be at most one problem on it. Whereas the conclusion, you'll have to do more than once on the test. So now is, what does it mean to have a p-value of 0.004? Okay, so how do we interpret this p-value? Okay, P, as I mentioned earlier, stands for probability. And here's what I can say. Okay, it's not the same as confidence intervals. Okay, that was a probability also. That was like a 95%. This is pretty different. And here's what we can do. And we could say that if the pH, the population mean, pH is 7. And if we conducted another study of, okay, and now I need to go, because I don't remember exactly, but it says somewhere 583. Okay, it's a lot of samples, by the way. Okay, again, this is many years with many, many people volunteering. So 583 water samples from many creeks. Then there would be a 0.4%. So I took 0.004, turned it into a percent. So 0.4% chance that the sample mean would either be, and now let's go and look at these numbers again. We got about, I'm gonna take one decimal place, 6.9, would either be less than 6.9 or greater than 7.1. How did I get 7.1? Any thoughts? Here's a hint. The pH is supposed to be 7. We got 6.9. Where did I come up with 7.1? It had to do with those two other numbers. Anyone see it? Okay, here's another hint. 6.9 is 0.1 below 7. How do you think I got 7.1?
You add 0.1.
Exactly. So the idea is we're doing a two-tailed test because our hypothesis had a not equal to. So that means we're looking at the left and right side. Okay, so you look at the mirror reflection. Okay, so again, 6.9 is 0.1 below, 7.1 is 0.1 above. So it's both sides. Another way of saying the same thing is you would say that there would be a 0.4% chance that the sample mean would be at least 0.1 away from 7. Okay, that's exactly the same thing. Any questions on interpreting, interpreting the p-value? Okay, now I'm going to interpret the level of significance of 0.1. Okay, and the good news, especially since I'm typing, is I can mostly copy and paste all the way up to there would be a. So I'm going to do that. And I could say if the population mean pH is 7, and if we conducted another study of 583 water samples from many creeks, then there would be a, and now it's a 10% chance, because 0.1 is 10%. So there'd be a 10% chance that we would end up falsely concluding that the pH differs from 7. And actually, let's go population mean. pH differs from 7. So if the pH was 7, then there's a 10% chance that we're going to end up saying, it differs from 7. Okay, and that's bad. That's a type 1 error, by the way. So the level of significance is the probability of a type 1 error. Any questions? Any questions on this example? It's a lot of steps. Any questions at all on it? Okay. Let me do another example. So this was an example for mean. I only have so much time to do so many, but you know, there are many, 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 many examples that could be done. Okay, just going to note something. I'm going to do a piece of the example, just the part that I haven't shown you yet. So if we want to see if women are not drinking the recommended 2.7 liters per day on average. And here is a bunch of data that was collected in quotes, which means I made it up. And we want to run the hypothesis. I'm just going to say it quickly, and then I'll show you how to do it. And that is H naught would be mu is equal to 2.7, and then H1, and actually H1 would be mu is less than 2.7. I think I'll write that out actually. And H1 is that mu is less than 2.7. Notice this we don't have not equals, because if they're not drinking the recommended 2.7 liters, that means they're not drinking enough. So they're drinking too little. And that's an issue if you don't drink enough. Okay. So then you look at this, and I'll let you decide type 1 and type 2 error. You can think about it. But we have our data. So I'm going to copy the data. I'm going to go to the calculator. Okay, I'm going to show you how to use this calculator now. So if I have a hypothesis test for a mean, here I have data. If I had statistics, I'd use statistics. I have data. I put in my data separated by commas. And we have a less than. So I make sure I click on the less than. Sigma will almost always be left blank, by the way. That's only if you happen to know the population standard deviation, which you never do. Just let you know that. Okay. Mu naught was, again, that was the other side of the H naught. And the other side of the H naught was 2.7. So that's our mu naught. And I hit calculate. Okay. Notice you get a p-value of 0.03. Test statistic. T is, by the way, this is the test statistic. When I asked you for the test statistic, that says T. And that gives our answer. Okay. Let's suppose that we had decided that we wanted a 0.01 level significance for one reason or another. Okay. So suppose we decided on a 0.01 level significance. Well, we got our p-value was equal to about 0.03. That's over here. Well, 0.03 is greater than 0.01. And because of that, we fail to reject the null hypothesis. So the conclusion is very similar to the other. Before we had there statistically significant evidence. Now we say there is statistically insignificant evidence. Sometimes you'll also say insufficient. That's another way of saying it. Evidence to support the claim that the population mean amount of fluid that women drink is less than 2.7 liters. Any questions on the conclusion? Or any questions on how I use this calculator? It's pretty simple. Put in the data separated by commas, choose your less, greater than, not equal to. The first one's called a left tail, second is right, third is two-tailed. And hit calculate. Put your mu naught in and hit calculate. Okay, now that we have that, let me do one more example, because I do want to talk about the project. So I want to make sure I get to that. Actually, for the example, let me give you templates, just like I did for confidence intervals, because I think that might help you. Okay. And kind of a template for the solution, okay, for the conclusion, is there is statistically significant evidence to support the claim that the population mean, and then I'm going to write XXXXX. So, for example, the population mean pH in water that flows into Lake Tahoe is not equal to 0.7 or differs from 0.7. Or it might be the population mean amount of fluid that women drink is less than 2.7 liters. Okay. And then I have another template. This doesn't change much. What's the only difference between the first template and the second template? It's very subtle and very important. What's the only difference? I'll let you read it. Tell me the only difference. It's just 2 letters. That's a hint.
Significant and insignificant.
Exactly. Significant and insignificant. Okay. You get those confused and you have screwed up as badly as you can possibly get. Imagine a court case and you forget the IN. Well, guess what? You just put someone in jail that shouldn't be in jail because you forgot the IN. That would be like as bad as it gets. Do you agree? Okay. Or if you put the IN where there shouldn't be an IN, okay, that means that you just let someone go out and kill a bunch of people because they're murderers, but you like, oh, it was just an IN. So don't get them confused. So if the p-value is small, you have the evidence, statistically significant evidence. You can say, I got it. I published my paper. Person's guilty, whatever you're saying. I need to put money into the lake, whatever it is to protect. Okay. Whereas statistically insignificant means that we don't have evidence. We really don't know enough to do anything. And that's what insignificant evidence is. Okay. Sometimes it means you need a bigger sample size. Sometimes it means you just give up. If the p-value is very big, you tend to give up. If the p-value is close to your level of significance, but maybe a little bigger, then you say, I think I'm going to get a bigger sample size, because then you're still hopeful, but you don't have, your evidence isn't quite there, but you have some hope at least. Any questions? Any questions on this? Okay. Now the p-value interpretation template is if, and I'm going to write the null hypothesis is true. You should not write the words the null hypothesis is true. So if you look at what I wrote up here, for example, is if the population mean is 7, because that was our null hypothesis. Okay, population mean pH is 7. So if whatever the null hypothesis is true, in words, you put that in. And if another sample of, I'm going to call it XXX, so that might have been, 258, it might have been 23, whatever your sample size was taken, then there would be I put XXX probability, that's your p-value. Okay, and sometimes you'll say percent chance, which is the same thing. That, and then in parentheses, I write the results of the new study will be at least as extreme as the results of this study. So in the case with the pH in the water, that would be that the results of the new study will show that the pH is either less than 6.9 or greater than 7.1. Any questions on the p-value template? Okay, the level of significance template's very similar. If, and then I put in parentheses, the null hypothesis is true. So whatever the null hypothesis is saying, you put that in words. And if another sample of whatever your sample size was taken, then there would be a like 5% probability, or maybe 10% or 1%, depending on your level of significance, that the new study was result in falsely concluding that, and then I wrote in parentheses, the alternative hypothesis is true. And that might be falsely concluding that the pH is not 7 for the population mean pH, or that women are not drinking at 2.7, women are drinking fewer than 2.7 liters of liters of water for their population liter consumption. Any questions at all on this template? Okay, let me do an example with proportions. And I'm going to tell you, though, I made this up. So don't quote me on these numbers or anything, but I'm sure a survey could be done. Probably one was done. I couldn't find it. But do the majority of Californians think that Governor Newsom should be recalled? I don't know if you've been following the news, but there's all kinds of stuff going on, and they got enough signatures. And so we're going to have an election to decide whether he gets recalled or not, our governor in California. Okay. Suppose that 341 of the 674 Californians surveyed answered that Governor Newsom should be recalled. Run the hypothesis test. Any questions on the question? Okay, so let's write down H naught. Okay, so what's H naught in this case? What letter do I use? What letter do I use for H naught? What's the key letter? And it helps to think of the survey question. What are you going to ask these 674 people? And that helps you on the letter. Very similar to the confidence interval idea. So what letter should I use? Okay, so survey question would be, do you think Governor Newsom should be recalled? That would be the question. So based on that question, what letter do I use? Very easy to type in the chat box. It's just one letter. Or a word if you're using a, but it'll be a letter. I don't see jumping in. Okay. If the survey question is, do you feel that Governor Newsom should be recalled? Then if they ask me, I would say no, for example. And when it's a yes, no question, what is the letter we use for the statistics or the parameter in this case? Yeah, P. Okay, P for proportion. So it's not mu this time, it's P because it's a proportion, population proportion. Okay, and in particular, we want to show the majority of Californians think so. So the biggest number you can have that isn't a majority is 50%. So that's 0.5. Any questions on that? Then we're going to do H1. And that's going to have a P. What inequality? Is it going to be less than, greater than, or not equal to? The hint is the word majority. So is it less than, greater than, or not equal to? You can put in the chat box or you can say it. Yeah, this one's a greater than. Majority means more than 50%. So that's greater than 0.5. Very important you get the inequality right. Very important you get the letter right. And you get the 0.5 right. All right, so in this case, this is really political science. Type 1 error, I'm just going to say it because we don't have time to type everything out. But a type 1 error would mean that we ended up publishing in the news that the majority of Californians want to get Governor Newsom recalled, and we were wrong. That's bad. And if it's a type 2 error, what that would mean is that you did the survey and then you weren't able to find anything out. You know, you thought the majority did, but you weren't able to show the majority did. So you don't publish it. But you were right the whole time and you would have had a really good article. And they're both bad, but they're pretty equally bad. Any questions on that? Since the type 1 and type 2 errors are equally bad, use a level of significance, which is alpha, equals 0.05. Any questions on that? Okay. And like on tests and stuff, the key is you have to explain why. You have to talk about the type 1, type 2 error and say, this is why I used 0.05 or 0.1 or 0.01. And as long as your rationale is correct, I'm good. Okay. So it matters. Okay. So then what I'm going to do is I'm going to go to the calculator. It's 341 over 674. So if I go to my calculator, this is not about a mean. So I need to go back to the calculator menu. And let's see if you can tell me which one I'm going to use. What number? So which calculator menu item? Yeah, the 16 because we're talking proportions. That's where the P was. And it's a hypothesis test. So it's a hypothesis test for proportion. Okay, and then N was 674. Our X was 341. Our P naught was 0.5. That was that majority idea. Here we have a greater than. That's a right-tailed test. Okay, and hit calculate. By the way, notice that this is Z. And it's Z because we can use the central limit theorem. NP and NQ are both bigger than 5. If they're not, don't even do the hypothesis test. Give up. You got to have NP and NQ greater than 5. So in this case, NP is just 341 because it's the number of yeses. And NQ is 674 minus 341, which is definitely bigger than 5. Our test statistic is Z. This is a normal distribution, so we use the letter Z. Is 0.308. Our p-value is about 0.38. So in particular, our p-value equals 0.38. Let me double check. Yep, 0.38. And that is definitely bigger than 0.05. Now, if it's bigger, then we say there is statistically insignificant evidence to conclude that, and now we can just say And I'm going to write the majority of all. Okay, I will take off a point if you don't emphasize that it's the whole population you're talking about. And that's why I write all Californians and not just the Californians that we asked, not the 674. This is all 40 million or so, or how many million of us Californians there are. Think that Governor Newsom should be recalled. And there's, let me boldface the in, because that's really important. So there's insignificant evidence to conclude that the majority of all Californians think that Governor Newsom should be recalled. Notice, insignificant evidence is the same thing as saying we ended up not knowing anything. Okay, our p-value is pretty big. Okay, it's much bigger than 0.05. This is one of those where you'd say, well, it may not be worth it to do another study. And you can't do a study with the same sample size, because if you do that and you do it 20 times, then it's more than likely you're going to have one of them that say that it is, which means that you get a type 1 error, which is bad. So you actually have to get a much bigger sample size if you're going to do it again in the real world. Okay. Any questions at all on this example? Okay. And just to know, I'll say it, but not type it, because I said it's less important, but it's something you should still know. And that is that if you want to interpret the p-value, then you would say that if exactly 50% of all Californians think that Governor Newsom should be recalled, and if we asked another 674 Californians, then there would be a 38% chance that at least 341 of them would think that Governor Newsom should be recalled. Okay. And our level of significance, very similar, is that if the majority of, if 50% exactly of all Californians think Governor Newsom should be recalled, and if we did another study of 674 Californians, then there'd be a 5% chance that we would end up falsely concluding that the majority of Californians, of all Californians, think that Governor Newsom should be recalled. Any questions on this example? Any questions? Okay, if there's no questions, I want to do the next big thing, and that is the secret word. And the secret word is statistically, because whether it's significant or insignificant, it's statistically significant evidence or statistically insignificant evidence to conclude da, da, da. So the secret word is statistically. All right, now comes the next piece of what we're doing today, which we'll spend 10, 15 minutes on probably. And that is talking about the project. So let's go to the syllabus. And in the syllabus, just a few things to note. The first thing is project 2 is due by June 6th. Okay, I know it's a while from now, but a lot of people like to start early. So that's why I like to talk about it early enough so that you could at least get started, even though if you don't, you'll know next week, you'll know all the details of the statistics, but now you at least should have all the ideas. Okay, so it's due June 6th. Same, by the way, it's the same percent in terms of your course grade as project 1. It's actually the same as your exams too. Okay, the final has the most percentages, but the project 2 is a big percent. So take it seriously. I want to remind you another thing, and that is there's a big penalty if you don't work with a partner, and better is to have 2 partners. So make sure you got partners. We talked about that last week, so just want to remind you again. If I click on this project 2 link, then I'm going to get into what project 2 is all about. All right, so the purpose of project 2, and I want to highlight this because it's important. A lot of people just don't focus on this, and you need to. is confidence intervals and hypothesis testing. Okay, so the hope is at this point, even though you're not experts in it, because I've just talked about it for an hour, but you haven't actually practiced, but the purpose is to come up with a confidence interval and conduct a hypothesis test. Okay, that is the biggie. Okay, and it has some similarities to project one and many differences, just note. So one similarity is you have partners. That's the same. You can have different partners, but you have to have partners, partners, 2 or 3 in your group. Okay. And I want to let you know that today I talked about the order at which you do hypothesis testing. So who remembers the very first thing you do for a hypothesis test? Pretty basic, because I've done a bunch of examples. So what's the very first thing you do for a hypothesis test?
You form the hypothesis.
Yeah, but I'm going to make it plural. You form the hypotheses because you can have a null hypothesis and an alternative hypothesis. So you're right. You form the hypotheses. You write down H naught and H1. Okay, so that's what you're going to do. And when I say write it down, when I say you write it down, if we were in the South, I'd say y'all write it down because it means you and your partners write it down. Okay, don't do everything by yourself. Make sure that you've talked to your partner, or you've talked to your partners, and you're in agreement that this is what you want to do. Okay, you need to identify a client. We talked about that in project one. Same idea is that if no one would be interested, then you don't have an interesting project. You need a different project. So again, you don't have to get paid, but imagine you're getting paid. That's the idea. Okay, or hired. So identify a client that would be interested in your results. Okay, so that's the first thing is you do that. The next thing you do is make sure that you're going to be able to get your data. I don't say get your data, but just make sure it can. Okay, so again, we're in COVID time, so a lot of data is harder to get. Just let you know that, but make sure it's possible. Then after that, and this is really important, go to the Project 2 discussion board and post your idea. So post your H naught, post your H1, post how you're going to get your data, and I'll look at it and let you know if it's going to work. And also I will let you know if it's not perfect in terms of working, I'll let you know what modifications you need to do to make it work. Any questions so far? Okay, I do want to mention that the project actually is on chapter 10, and we're not there yet. But I think I can explain it to you, even though I don't want to explain all the details today, but at least you'll get what's going on. Chapter 9 was hypothesis testing, and chapter 8 and 9 actually were confidence intervals and hypothesis testing for a population mean or a population proportion to decide whether a mean was bigger than some known number, or what does that mean? What is that proportion in terms of kind of a, boundary, low and high boundaries? Okay, chapter 10 is about comparison studies. So it means that you have 2 things you're comparing, and it could be 2 populations you're comparing, or it could even be the answers to 2 survey questions, or it could be 2 things that happen, and they have to be comparable. So you can't, for example, you can't compare height versus weight. Okay, because let me ask you, am I taller than I am heavy? It's a stupid question, isn't it? Doesn't mean anything. So that's why you can't do height versus weight. Okay, but you could do, for example, something like weight of men versus weight of women, because that's comparable. It makes sense to say, well, I think men are heavier than women on average. Okay, Okay, now that one might be a kind of a boring one because we all kind of already know that. But that's one. And now here's a big, big difference between project one and project two. A main focus on project one was a sampling technique. Okay, that was a big deal. And that's where like maybe 25% of your grade lied on whether you described your sampling technique done right. Okay, project two, that is very minor. You quickly describe it and that's good enough. Okay. And project one, I told you had to do either stratified sampling or you had to do cluster sampling. Project two, you could do whatever you want, including convenience sampling, as long as you admit to it. But it's important you admit to it. Okay, so if you do convenience sampling, that's not a problem. Okay, as long as you admit to it and just mention the bias that's going to happen because of it. Okay, you don't lose points for doing convenience sampling. You lose points for not saying you do convenience sampling. Any questions on that? But you don't need to write a whole paragraph on the sampling technique. That's like a sentence or two. That's a very quick part of the project. Any questions on that? Okay, the other big part that's a big difference is in project one had to be a survey where you asked people a survey question. Project two, you're just collecting data. Okay, it doesn't have to be a survey question. So for example, if you wanted to go and talk to Keep Tahoe Blue and maybe compare the data that was done in the last 10 years versus the data that was done 10 years before that. So if you wanted to look at 2012 to 2021, and you want to compare that to 2003 to 2012, and they sent you a spreadsheet with the Excel data, that's fine. Okay, you don't have to go and do a survey. You could just get their data, and that's great. Okay, any questions on that? And it's easy. Okay, and they'd be happy to send you data, by the way. Okay, and you'd have all that data. So you're allowed to have data that's just grabbed that way. Just like project one, though, if you can do a census, so if you can get the entire population, then it won't work for project two. Because there's no reason to run a hypothesis test and do a confidence interval if you know what the whole population is. Because you're 100% confident if you know the whole population. Any questions on that? So the whole population needs to be much, much bigger than your sample size. I would say at least 20 times bigger is kind of standard. Any questions on kind of that piece of it? Okay, so after you have come up with your hypotheses, put it in the discussion board, looked at my comments about it, and made sure it works, your next step, and actually even maybe before you even post, you could talk about a type 1 and type 2 error, because that you could do before you do that before you collect your data, and you decide on your level of significance. Then the next step is you get your data. And that should be quick. It should not take a long time to get your data. If it does, then you're wasting your time. Okay, it should be quick. Sometimes it's just a quick grab from the internet, the numbers, and remember it's a comparison study. Okay, other studies that people have done is they've done like prices at Amazon versus prices at small retail shops, and they wanted to see if Amazon's cheaper. Do you see how that's a comparison study? And Amazon sells, thousands and thousands of things. So the population's big, you're not gonna be able to get them all. And then you go grab, as you might guess, more than 30. Got to get more than 30 for your sample size. And you grab it. Okay. So whatever you have to be doing, that's what you do. And you can do a study where you're asking people. But the same thing with project one, two main things. One is you're not allowed to ask children. Okay, no surveying children because that's against the law. And the other is you have to have a sample size greater than 30. Okay, can't ask children, sample size greater than 30, and you have to in your paper, you have to talk about what you did. That's all. So those are the main things for the sampling that you have to do. Okay, then comes the next piece. And let me show you. The next piece is to go to the spreadsheet. Okay, and it's exactly the same spreadsheet. So if you already made a copy of the spreadsheet and it's in your Google Docs, you've got the spreadsheet. You don't have to do it again. Here's what you do need to do. And you'll see at the bottom, there's tabs. You'll see there's one Veristats, two Veristats, regression, chi-squared, ANOVA, there's others too. If you go to two Veristats, because this is a comparison study with a first variable and a second variable. And you're going to put in your data into your two Veristats. Okay, then what you're going to do, and this is something that I'll explain next week because we're not there yet, but you're either going to be using what's called independent or you're going to be using what's called dependent. And that I'll talk about next week. I'm just not even going to go there, but let you know you're going to go there. You're going to run your hypothesis test. You're going to get your confidence interval, okay, which is mostly done for you, okay? And remember, you should have already decided on your level of significance. Level of confidence, you do that later. So level of confidence, you do later, okay? And you get your confidence interval, you get your p-value, okay? You get your test statistic, which is T. You get your standard error. Remember standard error? It's either going to be this standard error for the mean independent, or it's going to be this standard error here, which for this particular data doesn't work, but it will for yours if you're going to be using dependent difference. And you get your standard error, and then you're going to have to interpret that too. Standard error to project 2 is the same as standard deviation to project 1. It is the main statistic that you have to analyze. Any questions so far? Okay, next. That's that one. There we go. So again, quickly describe your sampling technique. Summary statistic, standard error is the biggie. Kind of mean difference or the two means, those might be important. Don't go through, you don't have to go through all the stats. Okay. So it says, other than the means, you do not have to go into any detail about the statistics. Okay. And standard error too, because there's a whole paragraph on standard error. Okay. So standard error is a big piece. That's piece 1. Piece 2 is the confidence interval. Confidence interval for the difference. Okay. And I wanted to let you know, just like project 1, every time you discover anything, you have to mention what decision your client might make after discovering that. Okay, that'll be the standard error. That'll be the lower bound for the confidence interval. That'll be the upper bound for the confidence interval. Those are different. Not just the whole confidence interval, but lower and upper. Treat them separately. Okay. That'll be the p-value. That'll be the level of significance. It'll be the type 1 error, the type 2 error, the conclusion of the hypothesis test. Okay. Just a note for the confidence level, play around. Go to your percent confidence. You can look at 95, look at lower and upper, change it to 0.9. Look at lower and upper. Okay. And don't just look, but write about all of them. And then talk about, based on the pros and cons of each of them, which is best. And talk about which a client would want and why, and what the decisions will make. And will the client be okay with having a 90% level of confidence, which means you have a 10% chance of misleading your client. Okay. Whereas if you have 99% level of confidence, you only have a 1% chance of misleading your client. Okay. But again, if you go 99, you can have a much bigger margin of error, and that's a problem too. So you're going to have to talk about that. Okay. Another thing you're going to have to do is when you look at the p-value. Well, are you happy with it? Remember, you're trying to reject the null hypothesis. If the p-value is lower than level significance, you're probably happy about it. You got to reject. If the p-value is very high, you may not be happy, but it's time to give up. Okay, if you're losing a game by 50 points and it's soccer, you don't like try to play harder. It's over. You don't say, I'm going to play that team again. No, you suck compared to that team. Okay. On the other hand, if you're only off by 1, then you're going to say, we're going to do a rematch because I think I can still win. But the rematch involves a bigger sample size. If you don't do a bigger sample size, you can't do the rematch. You can't redo the study. Doesn't mean you have to do the study. Just talk about what you would do. Okay. And that's how p-values are important. Talk about the level of significance as why did they choose the level of significance? Again, the client is choosing the level of significance, but you're giving them recommendations. And then you're going to say how they would respond. So it's all about this client. The client is your audience. And you could assume the client understands statistics. You don't have to go into the equations. Any questions on that? Okay. And then very minor, you could talk about why your topic's important. You can talk about kind of how you would do delving deeper into the topic. That's kind of minor, but definitely make sure that the confidence interval and hypothesis test main points are in your conclusion, because that's the main piece. Okay. I also have a link to feedback on project 2 drafts that I'll let you look at. And I recommend you looking at that. Same as project 1 is that if you send it to me at least a couple days before it's due, okay, at least by Thursday, actually, not a couple days, but by Thursday at 8 in the morning, then I'll look at it and I will give you lots of feedback. Okay, if you don't send it to me, then I'll look at it and I'll give you a grade because you'll send it to me when it's due. I'll look at a grade and it won't be as good as had I told you, here's the 10 things you need to change. You change the 10 things and guess what? Your grade's going to go up because you fixed a lot of the problems. Okay, so that's, don't wait until that Sunday to start writing your project. That would be a disaster. Okay, you should be writing it in the next few weeks and then get it to me. I recommend by that Wednesday even. Okay, so you get it. It'll be first come, first serve, just like before. Okay, that's about it. I'm going to stop the share. I'm going to stop the recording.